Hello students, welcome to this lecture. In the last lecture, we were discussing about the basis sets. We saw that Hartree-Fock equation with the help of Ruthan's idea of introducing a basis function or thereby solving the Hartree-Fock-Ruthan equation, we could deal with larger systems, many electronic systems. That is because the Hartree-Fock-Ruthan equation, when it is formulated in the matrix form, becomes very convenient for its numerical application. Now, therefore, the idea of basis set is very important in any quantum chemical calculation. In the last lecture, we looked at different possibilities of basis functions. We started from hydrogenic functions. We looked at its, we discussed about its shortcomings. We talked about the Slater type of orbitals and then Gaussian type of functions. Then we came to this conclusion that perhaps it is the best computationally efficient if we use multiple Gaussian type of functions to represent one Slater type of orbital. So, therefore, we introduce the so called contracted Gaussian type of function, and in this lecture we will look at the basis functions for several different atoms and how we can obtain how we can use them for our calculations. All right. So, the first thing that we will discuss in this class is the STO3G for carbon atom. In the previous lecture, we discussed about the STO3G basis for hydrogen atom. Hydrogen atom has one electron, so therefore its electron is present in one s orbital. So, we only had to worry about the 1s orbital of that atom. Now, in case of carbon, since we have got 6 electrons, the electrons are present in 1s orbital, 2s orbital and 2p orbital. So, now we have to worry about basis functions for different orbitals. 1s will have different quality than 2s and 2p. So, therefore, the problem is slightly more complicated, but the basic idea remains the same, that what we call is the contracted Gaussian functions, or in particular we will see that STO3G, because we saw that by taking 3 different Gaussian functions, it was we were able to fit to a single Slater type orbital beautifully. Now, before we look at these numbers and find out what they are, let us have some basic ideas. So, what we want? We want one Slater type of orbital for 1s orbital, one for 2s orbital and one each for 2px, 2py, 2pz. So, therefore, we have essential orbitals are 1s, 2s and 2p. These 3 type of orbitals, we want to define them in terms of a Slater type of orbital. So, when we combine them, essentially we need 2 s type of orbitals, Slater type of orbitals, which is written over here in this red color within a square bracket, and 1 p type Slater orbitals. Since we are talking about the Slater type orbitals, this together is given in this square bracket 2s 1p. So, this is the definition of how many Slater type of orbitals we are representing in this particular basis form. Now, when I represent this one, that means I take one Slater type orbital for each atomic orbital, including the core as well as the valence. At the end, you would see that I will construct 5 different Slater type functions, because p orbital will have px, py, pz. So, they will have simple difference of the prefactor x to the power I or y to the power j or z to the power k that we discussed in the last class. But the Gaussian type of the Gaussian part will remain same. So, therefore, we will have 3 functions for p type, 1 each for s type. So, together we will have 5 functions. So, in this case STO3G, k, that is number of basis function, becomes 5. But we have decided that we will express these Slater type orbitals in terms of 3 Gaussian functions. Now, that is why when we write that in terms of the Gaussian type of functions, the Gaussian type of orbitals, we require 3 functions, 3 Gaussian functions for the 1s, 3 Gaussian functions for 2s and similarly 3 Gaussian functions for 2p, but in this case each 2px, 2py, 2pz. So, at the end, when I calculate how many s type of Gaussian functions I have, 3 over for 1s, 3 for 2s, so together 6s, and how many p type of Gaussian functions I have, I require 3 number of p types, but I know that each of these p type would also have 3 different components. So when I count these Gaussian type of functions, I write them in a round bracket as opposed to the square bracket what I did when I was writing number of Slater type orbitals. So what we want to do here, the contraction scheme, because we are trying to construct this contracted Gaussian functions, this contraction scheme becomes that we want to convert this 6s type of Gaussian function, 3p type of Gaussian function to 2s type or Slater type orbitals, 1p type Slater type orbitals. So this is the contraction scheme that we want to achieve with this STO3G basis set for carbon atom. Now let us look at, in the last class we discussed about this website from where you can download these different basis functions for different atoms. So I have taken from the very same website for the carbon atom and STO3G basis function. So now you see, first thing that you notice that the numbers are written in 2 different blocks. So this represents the element, the carbon, and then the next one is S, or here SP. This tells about the orbital angular momentum, S orbital or S or P orbital. If I had d electrons, if I had an atom in with d electrons, then I would also have SPD. Now this first block talks about the 1s orbital. What is the function? Now if I write this, the first Slater type orbital is obtained by using these 3 Gaussian functions. Let us find out what do we mean by these 3 Gaussian functions. The numbers that you see here in the second column are the coefficient. The number that you see in the first column are the orbital exponent. So using these 6 numbers, I can construct this 1s Slater type orbital or 1s contracted Gaussian type of function as the following. So I am taking 0.15, I am just excluding the numbers just to have this equation little readable. So I have 0.15 as the coefficient multiplied by e to the power minus 71 r square. The next term is 0.53 into e to the power minus 13.04 r square. So this way I can construct, this is one Gaussian, this is another Gaussian function, this is another Gaussian function with particular coefficients, particular value of coefficients 0.15, 0.53, 0.44. When I take this, I can construct a the sum of these 3 functions would actually be the best representation of one Slater type of orbital. Of course, this would still have some difference from the real real Slater type orbital, which has e to the power minus zeta r type of structure, but this combination is the best fit for a Slater type orbital. Now this is about the 1s. When we go to the second shell, 2s and 2p, both orbitals have electrons. So now what happens is that we normally take same value of the exponents in the Gaussian function, but use 2 different set of coefficients. So the first set of coefficients, so you can see here zeta I. So this column is for the exponent, this column is for coefficient, the third column is also for coefficient, but third column is not present in the first block because it has only 1s. When I am coming to 2s, so these coefficients are for the 2s orbital, these coefficients are for the 2p orbital. Using these coefficients, I can simply write the C1 e to the power minus zeta 1 r square plus C2 here 0.39 into e to the power minus zeta r square and so on. And similarly, taking this set of coefficients, I can construct the 2p orbital, Slater type orbital. Now, one important thing that you would notice immediately here is that look how different these exponent factors are for S type and 1s type and 2s or 2p type. You see a very large number of 71, 13 large orbital exponent simply indicates that the function will decay very fast. That is something that is desirable because 1s orbital, the electron in the 1s orbital is not likely to be found far away from the nucleus. So therefore, for 1s orbital, it is important that we take larger value of orbital exponent, whereas when you are talking about the valence orbital, these electrons are going to participate in chemical bonding. So therefore, smaller exponents there allows the diffusion of the electron away from the nucleus, which is essential for, let us say, for chemical bond formation. So these features are always present. You would see that the core orbitals would tend to have larger orbital exponent. Now, one thing that you would notice here, that if I had used Slater type orbitals, I would have taken only 5 functions. But since I am taking Gaussian type of functions as a contracted scheme, I am taking 6s plus 3p, so that is 3 into 3, 9, so 15 functions. Instead of 5 functions, I am actually taking care of 15 functions, but of course these are 5 Slater type functions, these are 15 Gaussian type of functions. Even though I am taking more number of functions, still computational expenses would be much less when I express these Slater type orbitals in terms of 15 Gaussian type of functions instead of taking these 5 Slater type of orbitals. Why so? Because we have seen this beautiful quality of this Gaussian product of 2 Gaussians is a Gaussian. So that makes our life much simpler, even if we are carrying more number of functions, but overall integral evaluation, especially when there are more than 3 or 4 atoms, becomes much more efficient when we use these GTOs as the basis function. Now, with the combination of this STO and GTO, the calculations became very competitive and things were looking good. Now, immediately one would realize, okay, fine. So, if by introducing GTOs, our calculations are now cheaper, why consider only one Slater type of orbital for one orbital? Let us say here, for example, 1s orbital, instead of having one Slater function, we could have taken 2 or 3 Slater functions, and for each Slater function, we could have done a Gaussian, contracted Gaussian type of functions. That is something that we normally do. We in fact take more than one zeta Slater type orbitals to describe one atomic orbitals. For example, is considered 2p or 2s. Instead of taking a single Slater type orbitals, we can take 2 or even 3 or even 4 Slater type orbitals. By Slater type orbitals, what do I mean? I mean I would have 4 different Slater type functions with 4 different exponents. So essentially the zeta values would be different. So that brings to this idea that instead of having these single zeta functions, as we have discussed here, let us have double zeta, let us have triple zeta to represent each atomic orbital. Now, this triple zeta or double zeta is being told in the context of the Slater type of function. But the moment you have double zeta functions, each Slater type orbital with 2 different zeta orbital exponents will have also the Gaussian components within them. So, this way we can actually make our basis set better. But as you would also realize that when it is not so clear for the carbon atom, but when you go down the periodic table, you would see that more and more number of orbitals would actually end up in the core part. Let us say you go to the 3rd row or 4th row. But we know that most chemistry happens with the valence electrons. So therefore, if we express all these orbitals as 2 or 3 different Slater type functions, then it is we are actually using lot of computational resources for those orbitals which are not going to contribute much. So therefore, what was proposed, that let us split the core from the valence. Consider the core electrons separately and the valence electrons separately, and this gave rise to this idea of the so-called split valence basis. Now, we'll again look at these numbers carefully, but this we'll just have some general discussion about split valence. Normally, the notation for this split valence is, you can see this is so-called 321G basis function. The common form of this split valence function is given as like this: K, there is a hyphen, LMN. This K, LMN are often usually denoted by some digits, numbers, and then at the end there is this G. Now, we'll look at what this means. First thing is about K. This K number would indicate how many, so the first number is about the core orbitals. This K, the value of K, whether it is 3 in this case or 6 or whatever number would come up, that would tell me that for the core orbitals, I am defining one Slater type orbitals, but this Slater type orbital is being expressed in terms of how many Gaussian type of functions. So the answer is that I am using K number of Gaussian type of functions to describe one Slater type of orbital for each core orbital. So this K number represents that core orbitals, you are taking one Slater type orbital always, and how many Gaussian functions are you using to describe this one Slater type orbital. Now, the next thing is this dash sign or the hyphen sign. This indicates the core valence separation. So, core part is finished. Now, whatever comes is for the valence. Now, in next 3, in this case, you would see that some digits, sometimes it is 2, sometimes it is 3. So, the next, how many digits, whatever number of digits you see, whether mostly it is 2 or 3, the number of digits tell number of Slater type orbitals that you are taking for each valence orbital. So, remember we are talking about double zeta, for example. In that case, we wanted 2 zeta functions to describe one orbital. In such cases, I would have 2 different a 2-digit number over here, like here you see 2, 1. That would tell that my valence orbitals are being expressed as 2 Slater type of orbitals with 2 different zeta values. Now, while the number of digits present here tell me whether it is a double zeta or triple zeta, the explicit value of the digits, that is the value of L or M or N, tells me how many GTOs or how many Gaussian functions am I taking to describe those many Slater type orbitals. Now, for example, consider this 3, 2, 1 G. So, this would tell me the first digit is 3, that means I am taking the 1s, that is the core orbital. In this case, I am talking about nitrogen. So, nitrogen's 1s orbital is being expressed in terms of 1 Slater type orbital, but this Slater type orbital is being expressed in terms of 3 Gaussian functions. Then comes the separator, then I have 2 digits. So, that means I have a double zeta potential. Now, so this is about the core. This is about the valence region. The core region is defined by these 3 Gaussian functions, the coefficients, the exponents, the coefficient and exponent. So, these 3 functions will represent the core of the 1s orbital. Now, we are going to the valence part. Valence part, I immediately see that there are 2 digits after minus hyphen sign. So, that means this is a double zeta. That means 2s and 2p orbitals are being expressed in terms of 2 zeta functions. Now, where are these 2 zeta functions? So, this second part of the function is over here. Now, you see there are 2 zeta functions. This is one zeta function, the other is the second zeta function. Now, each this zeta function or the Slater type of function is being expressed by how many Gaussian functions? The first one is being expressed by 2 number of Gaussian functions. So, this is number 1, this is number 2, this is the coefficient for the 2s, this is the coefficient for the 2p, and these are the 2 Gaussian exponents. Now, the second Slater type orbital is being expressed by only 1 Gaussian function. So, this is essentially a Gaussian function with orbital with the coefficient as 1 or the orbital exponent is given over here. So, this is a general anatomy of a basis set, but this 3 to 1 basis set that we see, this particular set of basis sets were proposed by Popel. So, they are also called Popel's basis set. Now, what we do is that we look at one more split valence basis. This time it is for carbon, but this is now 631G. So, again just to remind you, the first digit is talking about the core before hyphen. So, this tells that core orbital, that is 1s orbital, is being expressed in terms of only one Slater type function, but this Slater type function is expressed in terms of 6 Gaussian functions with these coefficients and the exponents. That is about the core. Then the separator comes, and then the next I see that there are 2 digits. So, that means I would have 2 different Slater type functions or 2 different contracted GTFs. So, the first is over here, second is over here. How do I know that? Because the first split valence, first Slater type function is being expressed in terms of 3 Gaussian functions. So, you have 3 Gaussian exponents, 3 coefficients for 2s, 3 coefficients for 2p. The second one is the second Slater type orbital is being expressed in terms of only 1 Gaussian function. So, again it is another Gaussian function. So, this is again 631G basis for carbon atom. Now, what we do is that we will establish its contraction scheme. Now, to do this contraction scheme, this is the scheme it is written down, but we will see how we are going there. Now we will look at this 631G. So we will first see that this is carbon atom. The valence or electrons, core and valence electrons are in 1s, 2s and 2p. So we are describing the core in terms of 1 slater type orbital. So therefore number of STOs is 1. For the valence 2s and 2p, each valence orbital is being expressed by 2 number of slater type orbitals. So 2, 2 here. Now coming to the number of Gaussian type of functions, the 1s orbital is being expressed in terms of 6 Gaussian type of function. The 2s orbital, which is being expressed in terms of 2 slater type of functions, is one slater type is expressed by 3 Gaussian, the other one is expressed by 1. So therefore together I have 4 over here, and similarly for 2p also there are 2 slater type function, one with 3 Gaussian, another with 1 Gaussian functions. So again 4. So when you look at the numbers in the square bracket, that is the for the slater type orbital. So I see that there are 3 s type of slater types, 1 for 1s, 2 for 2s, so that makes 3s, and 2 for 2p type of slater type orbital. So 3s 2p. What am I starting with? I am starting with 10s. How do I see 10? Because I see 6 of 1s, 4 for 2s, so that makes 10 of s type and 4 for p type. So therefore the contraction scheme became 10s 4p goes to 3s 2p. Now number of slater type of function, so in other words k in our calculation would become 1 plus 2 3, and this is 2p, there are 2, so but 3 such are there, so 3 into 2 6 plus 3, that makes it 9. So we for any other basis set we actually can derive this contraction scheme. All right, but there are much scope for further improvement in the basis functions. We will not go through them, but rather we will point out where what are the possibilities where we can improve our basis function. One particular thing is that the so called polarization function. See, when you looked at hydrogen atom and hydrogen molecule formation, you see we started with 2 1s orbital of hydrogen atom, but when the hydrogen molecule forms, we know that the atomic individual atomic orbitals, when they form the molecule, they actually get polarized. We saw a bonding and antibonding combination, right? So in other words, what happens? We need to have some p type of character in our starting basis function, so that it will allow the chemical bond formation, right? So for example, when 1s orbital was taking part in the bond formation, we required a polarization via a 2p orbital. So similarly, you can imagine when you are making a bond with respect to 2p, you would require a function of orbital angular momentum higher than the valence electron. So for example, if your valence electron is in L equals 1, you require L equals 2 or some d type of function into it, so that you have enough polarization, and that gives you freedom in the molecule to form different types of bonds. So this is typically done by adding some polarization function. So if your basis function you have with angular momentum L, then you add some additional basis functions with angular momentum L plus 1, and that is called the polarization functions. Normally when you add polarization functions in this K, L, M and G notation, you at the end you put a star. What is changing? I am showing it in red. So this star indicates that I am using a polarization function, that means a function of higher orbital angular momentum. In some specific cases, for example, very electronegative atom or an anion, where the electron is expected to be found far from the nucleus, when the electron is expected to be really diffused away from the nucleus, in those cases we require some special attention. In those cases, what we do not require is a function with higher orbital angular momentum, not a polarization function. Rather, for example, if I say that there is a p electron which is actually diffused, in that case what do I need? I need a special function which will be having p type of character, but its orbital exponent will be so small that this function will survive even at longer distance. So that is the best way to represent a diffused basis function. So when you are dealing with anions or electronegative atoms, or even we are talking about weakly bound complexes, in those cases diffused functions are necessary, and normally you just add another basis function with the same orbital angular momentum, but now orbital exponent becomes very small. that is that you get with the diffuse function, and where you normally denote when you are using this diffuse function with a plus sign before this g. G stands for the Gaussian contracted scheme. So, when it is star after g, it is polarization function. When it is plus before g, it is diffuse function. Now, whether we are talking about the STO3G or the split valence basis function, all these basis functions were constructed by looking at the Hartree-Fock wave function. So, Hartree-Fock wave function and Hartree-Fock energies were the quantities that were fitted to obtain these coefficients of the orbital exponents. But we would see that Hartree-Fock calculations do not incorporate all the electron correlations. So, there are a series of basis sets that use better electronic structure method to obtain these coefficients. So, therefore, they have new different types of basis function. They are called correlation consistent basis function. There is a series of basis functions called correlation consistent, that stands for CC. This is polarized, just the way we did. Polarized valence double zeta. So, this also says it is a split valence double zeta basis function, polarized, but all these coefficients and the exponents are being obtained from highly correlated methods. So, these basis sets are very useful when you are doing spectroscopic application of quantum chemistry. So, they become very useful. The other important quantities are the basis sets are the so called effective core potential. Now, if you think about the transition metals or the lanthanides and actinides, you would see that there are many electrons. So, that you have lot many core electrons, but most of the chemistry happens in terms of the valence electrons. But if we define all these core electrons even in terms of the split valence, then also the computation becomes heavier without getting any extra advantage. So, therefore, it was proposed that let us, for heavy atoms at least, let us construct different set of basis functions where the core orbitals or the core electrons would not be treated explicitly, rather they will be defined in terms of an effective core potential. So, individual identity of those electrons will not be there. So, all those electrons in the core will be defined by a standard effective potential, and that was called effective core potential. Whereas, the valence electrons will again be described in terms of the basis functions that we are using, the double zeta, triple zeta, polarization and all the features. In addition to that, there was also another need, because in heavy elements, the core electrons are of course inert for chemical purposes, but they also have an important contribution in particular to the relativistic effects. So, therefore, these effective core potentials, when they were designed in such a way that they also incorporate the relativistic effects that are present in these elements. So, that way effective core potentials are very useful when you are talking about heavy elements, in particular the metal ions or metal complexes. So, one famous basis function along that line is the Los Alamos National Laboratory 2, and that is the name of the effective core potential, and the double zeta is the basis for the valence electron. So, together you talk about the core and valence together. Most of our discussion has been focused on molecules, but then we have seen that, let us say, in extended materials for periodic systems, let us say you have several metal centers. In those cases, these atom center basis functions are not very helpful. In those cases where we have periodic materials where the electron is let us say delocalized over an extended period, extended range of space, in those cases we often use the valence electrons as free electrons. So, to treat those kind of systems, we have completely different set of basis functions. They are called plane wave basis functions. In condensed matter theory, you require this plane wave basis function for those kind of systems. But for molecular calculations, we can live with the basis functions that we have discussed. So, in this lecture, we looked at different forms of basis function. We had investigated, or we in detail about how to identify different basis functions, what are the coefficients, what are the exponents, and what they represent, how they control overall chemical bonding. And this way we realize that this effective the basis functions in general, and also the effective core potentials for heavier elements, they play a very important role in the success of quantum chemistry. Thank you for your attention.